What is the nature of our universe? How did it begin? How did we come to be? From the dawn of our existence, in many different ways, we have speculated about the nature of the universe. Hello, I'm Nichelle Nichols. When I played Lieutenant Uhura on the starship Enterprise, we ventured where no one had gone before. That was science fiction, of course. Now I want to guide you on an equally fascinating exploration of the unknown and invisible with another kind of ship, a telescope that makes pictures of the hottest places in the universe, places that shine with the light of X-rays. Why do we want to see these hot places? Well, imagine that this freeway represents the universe, and the big trucks on it are all the stars and galaxies that we now observe with our wonderful optical telescopes. We would be able to learn much by observing the trucks, their size, shape, and power, the length, width, and topology of the roadway, the directions, interactions, and speed of the trucks. But many of the trucks' motions would be puzzling. We would see changes in speed or lane changes. We wouldn't know that what happens on the freeway is largely determined by another, hotter component: cars. They zip in and out and make up most of the mass on the freeway. In a similar way, much of the action in the universe is caused by matter so hot that it shines, not in visible light, but in X-ray light. This matter can be in the form of colossal 50 million degree clouds of gas in galaxy clusters, or in multi-million degree bubbles of gas produced when a star explodes, or in matter that has been heated to hundreds of millions of degrees as it swirls close to the most bizarre of cosmic objects, a black hole. The only way to see this hot universe is with an X-ray telescope. It is the 22nd of July, 1999, at the Kennedy Space Center in Florida.
Launch Director, you have the MMT concurrence to proceed with the launch.
The crew of the Space Shuttle Columbia, under the direction of Colonel Eileen Collins, America's first female space shuttle commander, is ready to go.
Ground 2, how do you read?
CDR, loud and clear.
Columbia's payload is NASA's Chandra X-ray Observatory. The Chandra Observatory is the most sophisticated X-ray telescope ever built. It is named in honor of Subramanian Chandrasekhar, or Chandra, as he was called by his friends and colleagues. Born in India in 1910, Chandra immigrated to the United States in 1935 and joined the faculty of the University of Chicago in 1937. Fellow astrophysicist Jeffrey Burbidge fondly remembers Chandra's intellect and work ethic.
He was the hardest working scientist I've ever seen. He
would work 12-hour days, basically 7 days a week. He used to come in at about 6:30 in the morning and start work. And I vowed that somehow I would get in there ahead of him. I finally achieved that by staying up after observing it. Chandra was one of the great figures of this century in astronomy and in astrophysics. And not only that, but much of his work is related to phenomena that we now are exploring in the X-ray.
Chandra's elegant applications of the laws of physics to astronomy transformed our view of the universe. In 1983, Chandra received the Nobel Prize in Physics for his work on the structure of stars, work which began when he was a young man. While still in his 20s, Chandra made a fundamental discovery about white dwarfs, the collapsed remnants of burned-out sun-like stars. He used two revolutionary new theories of physics, relativity and quantum theory, to show that white dwarfs have a maximum mass, which came to be known as the Chandrasekhar limit. Beyond this limit, there exists a realm of exotic physical extremes, a high-energy realm that Chandra is designed to explore. As we shall see, this remarkable telescope was not built in a day. Its creation was a modern-day odyssey that spanned more than 2 decades. In 1949, a group of scientists led by Herbert Friedman launched an X-ray detector aboard a V-2 rocket.
The moment has come. Main stage.
When the rocket arched high above the Earth, it gave astronomers their first fleeting glimpse of the hot universe. The X-rays they detected came from the sun. Scientists suspected that the sun might produce some X-rays, but until the space age, there had been no way to detect them. That's because above the Earth, in the thin upper reaches of our atmosphere, X-rays are absorbed when they collide with molecules of oxygen and nitrogen. Despite the hazards of space astronomy during these early years of rocket flight, Friedman's group was tantalized by the findings, and they continued to launch X-ray detectors to study the sun. Then, in the early 60s, a team of scientists led by Riccardo Giacconi built an X-ray detector that was 100 times better than previous ones. At first, they too were plagued by difficulties with 2 failed flights. Then, at 1 minute to midnight, on the 18th of June 1962, they had success. The rocket flew, and the payload worked properly. During the flight, Giacconi's group discovered a strong new source of X-rays. The strip chart recording revealed the source to be in the constellation Scorpio, so it was named Scorpius X1. It was hundreds of times brighter than anyone had expected. This astonishing discovery heralded the dawn of a new era of astronomy. With all manner of vehicles and instruments, scientists rushed to establish the new field of X-ray astronomy, and the discoveries mounted. Soon it became apparent that Scorpius X1 was not unique. But the pioneers of X-ray astronomy labored under 2 severe limitations. The rockets flew high enough to detect X-rays for only a few minutes at a time. And the X-ray detectors couldn't take pictures of the X-ray sources. The X-rays could only be counted and recorded on a simple graph-like plot. So Giacconi and his colleagues made proposals to NASA that would address both problems. They proposed putting X-ray detectors on a small satellite that would orbit Earth, and they presented a design for a telescope that could actually make pictures of X-ray sources. Late in 1970, they achieved their first goal. A small 140-pound satellite with an X-ray detector was launched from a platform off the coast of Kenya. It was the 7th anniversary of Kenyan independence, so the satellite was named Uhuru, the Swahili word for freedom. A member of Giacconi's team at the launch was a young scientist fresh from MIT, Harvey Tannenbaum.
At the time of the Uhuru launch, we knew about the existence of some 25 or 30 X-ray sources from rocket and balloon flights, and we didn't really know what the sources were. So we were very excited about the launch of Uhuru because we were going to survey the entire sky with much greater sensitivity, and we hoped to locate the sources with enough precision that we'd be able to find their optical and radio counterparts, and with the ensemble of data we might finally understand how all this X-ray energy was being produced.
Though small in size, the impact of Uhuru was huge. Hundreds of strong sources of X-rays were discovered. Some were identified with stars that had exploded, others with objects thought to be neutron stars. And there was good evidence that Uhuru had detected a black hole. One idea for finding a black hole was to look for X-rays that might be produced if a star and a black hole were in a close orbit, and matter was being pulled off the star into the black hole. The Uhuru team discovered such an object in the constellation of Cygnus. The data showed that X-rays were being produced by some invisible source that appeared to be so massive it could only be a black hole. Uhuru also detected X-rays that came from galaxy clusters. An intriguing possibility was that the X-rays were being produced by colossal clouds of hot gas in the clusters. It was now more clear than ever that a telescope which could actually make pictures of X-ray sources was needed to better explore these discoveries. However, many scientists were skeptical that such a telescope could be built. But one of Giacconi's team was undeterred by the skepticism. Leon van Spaebroek took on the challenge of designing the X-ray mirrors.
The fundamental difficulty with X-ray optics is that they will not reflect from a surface if they come into it at normal instance like this, which is, of course, the way we use optics in visible light, but in this case the X-rays would just penetrate into the surface and be lost. And so instead of that, they have to come in at a very shallow angle to the surface. This causes the optics to take on a characteristic barrel shape, and it makes them much more difficult to fabricate.
In the 1970s, a group led by Giacconi was awarded a contract to build a focusing X-ray telescope. Under van Spaebroek's guidance, 8 mirrors, each about 2 feet in diameter and polished to a tolerance of 1/10,000,000th of an inch, were assembled into the first true X-ray telescope and put aboard a satellite. The satellite, which was named the Einstein Observatory, was launched on the 13th of November 1978. For the first time, astronomers could see X-ray images of cosmic sources. Like Uhuru, the scientific impact of the Einstein Observatory was enormous. Young stars, exploding stars, black holes, vast hot gas clouds, and distant quasars were all found to produce X-rays. Other X-ray telescopes, most notably ROSAT, would build on Einstein's success. While these new telescopes revealed stunning vistas of the universe, their images still had limited resolution. So X-ray astronomers pushed to develop a telescope that would make images as sharp as those made by optical telescopes. To do this, Giacconi, Tannenbaum, and others made a proposal for a sophisticated X-ray telescope that would be the largest ever built.
It is the logical next step after Einstein. It is a much more powerful mission. It will have an angular resolution, a sharpness 10 times greater. It will have a sensitivity, that is the ability to see faint objects 100 times better. And it will allow us to do spectroscopy to 1,000 times better. So it will be together a discovery and a detailed study mission.
In 1981, NASA funded studies for this telescope, and it was given its first name.
AXAF, the Advanced X-ray Astrophysics Facility.
Harvey Tannenbaum became the leader of the scientific mission support team for the project.
In our 1976 proposal, Ricardo Giacconi and I had advocated building this 1.2 meter X-ray telescope in something like 7 years and getting it up and operating in space. And then on the basis of the success of the Einstein Observatory, the National Academy of Sciences Astronomy Survey Committee, chaired by George Field, gave the mission the endorsement as the highest priority new program for the 1980s. So at that point we were very optimistic. We thought that the program was on a fast track and we'd have it up and operating in space by the mid to late 80s.
Despite endorsement by the scientific community, mirrors of this complexity had never been built before, and there was concern that the substantial technical demands could be met. So Chandra's scientists were given a challenge.
Chandra mirrors were about 1.5 times the size of any mirrors that had been made previously and had tolerances that were of order of magnitude tighter. So there was concern that these mirrors could be made.
In the summer of 1988, the Congress, under the leadership of the House Appropriations Subcommittee, insisted that our team, NASA, our scientists and engineers at the Smithsonian, and the mirror contractor, Hughes Danbury, demonstrate that we could build the 2 largest mirrors in a time not to exceed 3 years, and unless we were successful, there wouldn't be an AXAF program.
Over the course of the next 3 years, the Chandra scientists set out to prove that the mirrors could be built. The results were encouraging.
The results of the X-ray test showed that the mirrors performed twice as good as the specifications, so it's clear that we had met the challenge, and in fact I think the whole process was critical for the program because this more or less trial by fire really helped us forge a real team, and we worked through the project as a team from there on.
Though the team had met the challenge and proved that the mirrors could be built, NASA had many ambitious projects on the horizon. And with a slowdown in the economy, the money simply was not there to fund all of them. The scientists were told that Chandra must be downsized or face elimination.
When we heard that they wanted to cut the program, we simply couldn't believe it.
I was extremely disappointed like everyone else. We felt that the observatory was almost virtual. It was that carrot at the end of the stick, except the stick was always the same length. The launch was way in front of us, and we would never get to it.
We had met this incredible challenge. We'd built the mirrors, and we had had a big party to celebrate, and we were looking forward to building the observatory, and we heard the program might be cut. And we really weren't prepared, and we certainly weren't willing to do that, and a real struggle ensued, and the success of the mission certainly hung in the balance.
After 4 months of extensive review and heated debates, a modified telescope program emerged. Chandra would have 4 pairs of mirrors rather than 6, and 2 primary scientific instruments instead of 3. Another important cost-cutting change was made at this time. Unlike the Hubble Space Telescope, which shuttle astronauts can work on, Chandra would not be serviced after launch. But the decision to forego servicing had a benefit. The telescope could be put in a much higher orbit than Hubble. This orbit takes the spacecraft a third of the way to the moon. The large orbit enables a single observation to last as long as 55 hours, allowing Chandra a better look at faint and distant X-ray sources deep in space. With restructuring complete, the project went ahead with renewed vitality. At Hughes Danbury Optical Systems, the mirror blanks were ground and polished to exacting tolerances. Completed ahead of schedule and under budget, they were the smoothest mirrors ever made. If the entire state of Colorado were as smooth as the Chandra mirrors, Pikes Peak would be less than 1 inch tall. The mirrors were then shipped to optical coating laboratories in Santa Rosa, California, to receive their reflective surfaces. First, they were cleaned repeatedly with specially formulated detergent and deionized water until they were virtually dirt and dust-free. Then they were placed in a vacuum chamber and coated with iridium, a highly reflective metal. The coating was a millionth of an inch thick and uniform to a precision of a few atoms. The mirrors were sealed from this point on, never to be touched again by human hands, as merely one fingerprint would cause permanent damage. They were then moved back across the country to Eastman Kodak in New York, where they were assembled into a support structure to become the high-resolution mirror assembly.
The integration of the mirror elements into a single unit was in fact an incredibly challenging engineering job. The mirrors are fragile, so you had to handle the glass very carefully, you had to keep it very clean, and the mirror elements as a whole weighed in at over 2,000 pounds, and so you were working with these relatively large, bulky, heavy, but yet fragile elements, and you needed to align them to tolerances that were measured in millionths of inches. And so these tolerances that we're talking about were dimensions that were much, much smaller than the thickness of a human hair.
Nothing of this magnitude and precision had ever been done before.
During the assembly of the mirrors at Eastman Kodak, we found that one of the mirror elements was just slightly out of alignment, and for a reason we didn't really understand. We traced the problem to a bank of fluorescent lights, and with the lights on, the temperature in the assembly tower, in the center of the tower, the temperature was just a few hundredths of a degree, just a small, small amount, a few hundredths of a degree warmer than the air further away. And that small temperature difference actually introduced a different amount of bending in the laser beam that was used to align the elements to each other. And once we understood the problem, we solved it by keeping the lights off. We literally didn't need them, and so we were able to put the mirror together in the dark.
Manufacture of these mirrors was a technically very challenging task, and many organizations contributed to it and worked very well with each other during this whole period. So we and the rest of our nation owe a great deal to people at Hughes Danbury Optical Systems and also at Eastman Kodak for doing very exquisite and demanding engineering in this task.
The mirror assembly was then delivered to Marshall Space Flight Center in November of 1996 to test how the mirrors would perform in space. Over the next few months, a specialized X-ray calibration facility was operated 24 hours a day as thousands of tests were made.
It was a bonding experience for probably 200 or 300 scientists. We essentially worked around the clock through Christmas and New Year's up into the spring and early summer. And with a few days off, we're changing out instruments and various technical problems that were no showstoppers, but lots of support equipment didn't always work as advertised, so we had to work around it. But the observatory and its instruments worked beautifully.
These exquisite mirrors, though a marvel in themselves, are only half the observatory. For their purpose is to bring cosmic X-rays into focus onto two specially designed X-ray cameras. One of those is the high-resolution camera.
The high-resolution camera is a detector that has two very important features that take advantage of the telescope we have. The first is that it takes a very, very sharp image. If we had the same telescope and the same detector, we could point at a stop sign 12 miles away and actually see the letters STOP. So that's the kind of sharpness we're talking about. And the other really important property from the point of view of X-ray astronomy is that each time an X-ray is detected in our detector, we'll be able to measure precisely what time that is. So we can begin to look at the variation of intensity of X-ray sources with a lot of precision. And there are some examples of X-ray sources like pulsars that are repeating a signal over and over again in a sort of a cyclic way. And measuring that very carefully and measuring changes in that very carefully is a very important part of the science we want to do. So very, very good images, which of course are the heart of the Chandra Observatory, plus very good time resolution at the same time, is a combination which is going to give us some really unique looks into what's going on in the X-ray sky.
The other X-ray camera is the Advanced CCD Imaging Spectrometer. It is an instrument that uses charge-coupled devices, or CCDs, and works much like the chip in a camcorder.
The CCD imaging spectrometer is designed primarily to record images and spectra at the same time. Things in the past that were all blurred together and we couldn't separate out the intrinsic properties will now be, for the first time, shown to us in great detail, both the images and the spectra at the same time.
In addition to these two cameras, the telescope has another set of devices called transmission gratings. When used with the cameras, the gratings give scientists detailed information about the temperature, motion, and abundance of chemical elements in X-ray sources.
The gratings are inserted in the path of the X-rays as they come off the observatory mirrors. The X-rays go through the grating and are diffracted left or right according to the energy of that particular X-ray. A high-energy X-ray is diffracted a little bit. A low-energy X-ray is diffracted quite a bit. So that if you place a detector and capture the image very precisely, you will know very precisely the energy of the X-ray that you're capturing.
The transmission gratings on Chandra are, in my humble opinion, going to be one of the most revolutionary aspects of this mission, and in fact will reveal scientific wonders that we have yet to imagine. The exquisite images, of course, will be unparalleled.
The instruments were installed in a control and electronics module at Ball Aerospace in Colorado. Then, the instruments and the mirrors, which were shipped from Marshall Space Flight Center, rendezvoused at TRW in Southern California. Here, Chandra finally became an observatory. The science instruments and the mirrors were integrated into the body of the spacecraft, the final home that provides the environment for the telescope to do its work. On the spacecraft, insulators and radiators protect the telescope from the extremes of space, keeping it at a uniform temperature at all times. Communications and data systems convert and transmit the precious information captured by the science instruments. And finally, an array of solar panels which extend like delicate glassy wings capture and provide all the energy needed to run the observatory. 2 kilowatts, about all the power used to run a portable hairdryer. After months of careful assembly and testing, Chandra the Observatory is ready to roll. It leaves TRW and crosses the country for the last time. Chandra arrives at the Kennedy Space Center to be prepared for its final journey into space. As the crew of the Space Shuttle Columbia looks on, Chandra is ready for flight. Later, it is secured in Columbia's payload bay. It will be the largest shuttle payload ever carried into space. Sunrise, 22nd of July, 1999. It is the start of another sultry Florida summer day. Eileen Collins, the first woman shuttle commander, leads the crew that will carry Chandra and its promise of a new vision of the universe into space. At 31 minutes past midnight on the 23rd of July, 1999,
20 seconds.
23 years after the project started, the
15.
final countdown arrives.
12, 11, 10, 9, 8, 7, 6, 5, 4, 3. We have a go for engine start, 0. We have booster ignition and liftoff of Columbia.
Seven hours later, with the shuttle safely in orbit, the payload bay doors open.
Center lines are coming open.
Columbia, Houston, you are go for deploy.
And we copy a go for deploy.
A small spring gently catapults the satellite into space.
Houston, we have a good deploy.
Roger, good deploy. Thanks for the words, Eileen.
You look out and you certainly know that it's moving towards you and over the head of the shuttle.
At last, the Chandra X-ray Observatory flies gracefully free.
I will tell you, there is nothing as beautiful as Chandra sailing off on its way to work.
Once Columbia is safely out of the way, Chandra is boosted into its final Earth orbit with a carefully timed sequence of firings. By the 12th of August, all the on-orbit safety checks have been completed. The moment of truth has arrived. From the Chandra Control Center in Cambridge, Massachusetts, a command is sent to Chandra. Some 50,000 miles away in space, a small explosive charge releases a bolt, and the 9-foot protective door in front of the mirror swings open. X-rays from the cosmos shine on Chandra's exquisite mirrors for the first time. Later, scientists hover around computer consoles and await the first image that will prove that Chandra is a revolutionary telescope. They will not be disappointed.
There you go. All right. Look at that.
Look at that picture. Isn't that amazing? We've come such a long way, and to get everything focused down to that one moment, it was a great feeling of elation. Right now, I'm going to watch the end of this maneuver, and I'm probably going to go home and sleep.
To the delight of astronomers and the world, NASA officials and the Chandra team soon presented proof that a new revolution in astronomy was about to begin.
This is a great day for the Chandra team, and it's a great day for all astronomy.
Last Thursday night, we pointed Chandra in the direction of Cassiopeia A. That's a supernova remnant, the aftermath of a violent explosion, and this is what Chandra saw. That's just a beautiful sight. Those of us who've worked on it just are absolutely enthralled with it.
Chandra is bringing the X-ray universe into sharp focus, giving us new insights into old questions. Questions about the origin of the raw materials needed to make planets and people. About the limits of space and time and the forces that shape our universe. It is here, at the largest gathering of astronomers in the country, that scientists eagerly await the first results from Chandra.
I'm going to get that all day tomorrow.
Unveiling breathtaking new vistas, Chandra scientists report on their searches for answers to cosmic questions.
The velocities have been measured up to as high as 4,000 kilometers.
You could probably find a way to make it work. Then the question is, will it predict something in the future and will it hold up?
This is the very beginning. We only got this data about 3 weeks or so.
Some prospect the remnants of exploded stars to locate rich veins of the heavy elements necessary for Earth-like planets and life. Some trace swirling, boiling hot gas near black holes. Other scientists focus their attention on distant galaxies to learn more about how the universe evolved. And some study teeming clouds of young stars to better understand what conditions might have been like when the Earth formed. One of the first images Chandra made was of a rich cluster of young stars in the constellation of Orion.
The Chandra image of the Orion Nebula is simply spectacular. There are 1,000 X-ray emitting young stars. This is the greatest concentration of X-ray sources ever seen. The stars in the cluster are generally 1, 2, or 3 million years old, which is extremely young in the lifetime of a star. When stars are very young, we have found they emit hundreds or even thousands of times more X-rays than when they're middle-aged. These stars are analogs of our sun when it was extremely young, and the X-rays from the young sun may have irradiated the disks, which then formed the planets. We're not sure, but recent studies suggest that when X-rays illuminate the disks around them, that it will transform the properties of the disks, and this may influence the formation of planetary systems. The Chandra observations should help us enormously to understand the origins of the X-ray emission in these young stars. Because we have 1,000 of them all at the same distance and all roughly the same age, we should be able to unravel the complexities that have confused us in the past.
When the solar system formed with its planets, including our Earth, it had a rich supply of the crucial ingredients essential for life as we know and enjoy: carbon, nitrogen, oxygen, and other vital elements. But where did they come from?
Heavy elements such as carbon and oxygen are synthesized at the cores of very massive stars, and they'd remain there if the cores of stars were stable. Luckily for life and the evolution of life, massive stars are not stable at the endpoints of their evolution. The heavy elements at the center of stars ultimately reach a point where fusion is no longer possible. The core collapses and generates an explosion which blows out the outer layers in a grand explosion we call a supernova. The explosion generates a hot, expanding shell of material both from the core of the star as well as from material swept up around the star. And this hot gas emits large amounts of X-ray radiation over tens of thousands of years.
Not surprisingly, some of Chandra's first targets were these hot remnants of supernova explosions. Claude Canizares and his team at MIT used Chandra's transmission gratings to make a detailed study of the remains of a massive star that exploded in a nearby galaxy. What they found was a revelation about the genesis of elements crucial to life.
Although there are very few of these massive stars in the universe, they provide most of the oxygen in the universe. There are roughly 10 solar masses, 10 times the mass of the sun, in oxygen alone. Now, there's very little oxygen by comparison in our solar system. So this is enough oxygen to eventually mix with other material and create the equivalent of thousands of solar systems. In that regard, these things might be called the real fountains of life, because it was an explosion of such a supernova that created the oxygen that permitted life on Earth.
The tremendous forces that cause such massive stars to explode can also leave behind a rapidly rotating, highly magnetized neutron star that emits beams of radiation and acts like an awesome generator. The electric voltages around a neutron star are 30 million times that of a bolt of lightning, and the total power output is equal to that of 100,000 suns. This eerily beautiful Chandra image shows a neutron star powerhouse at work, producing jets and rings of high-energy particles in a supernova remnant called the Crab Nebula. When the most massive stars collapse, the tremendous forces involved crush the star's core beyond the Chandrasekhar limit, beyond the neutron star stage, creating a black hole.
This table has a surface, or the Earth has a surface. Black hole has no surface. And the so-called surface of a black hole is the event horizon. And the event horizon, nothing can remain at the event horizon because the inward pull of gravity is infinitely strong there. And anything that passes through the event horizon must hurtle toward the center of the black hole and be totally destroyed. You can't see a black hole, but you can hope to see X-rays from hot material or gas that's just outside the black hole. It's falling toward the black hole. So if you want to find a black hole, the best thing to do is to find one that has a reliable and nearby gas supply that the black hole can capture. That's why looking at the centers of galaxies is really a good bet in terms of finding black holes and being able to really probe them.
The gravity from the black hole can be so strong that it actually pulls matter down into the black hole. Now, as this matter flows down into the black hole, it speeds up and it forms a flattened disk rotating around the black hole. As this matter rotates around the black hole, friction heats it up, just the way your hands get hot when you rub them together very fast. The matter near the black hole is going almost at the speed of light. If you imagine if you rubbed your hands together at the speed of light, they'd get really hot. Well, this hot matter emits X-rays, and with Chandra, we can measure the energy of the individual X-rays coming from this matter.
There is increasing evidence that giant black holes lurk in the center of most galaxies, including our own Milky Way galaxy. So, scientists brought Chandra's superior resolution to bear on the center of our galaxy, and through a thick haze of interstellar gas and dust, they were able to separate out the giant black hole from other X-ray sources nearby. When they examined their data, they were surprised.
The amazing thing that we've found is that this thing is absolutely very quiet. A 2 million solar mass black hole in sort of the normal context where we see them is at least 1 million times brighter than this, and maybe even 1 billion times brighter than what we're seeing here. So this is an extremely interesting result. The X-rays are just puny. So that's a real puzzle and is going to challenge the theorists to try to explain that, why it is so faint.
When astronomers observed our extragalactic neighbor, the nearby Andromeda galaxy, they found yet another puzzle.
In the very central region, this region here, which is about 30 light years across, we find 5 individual X-ray sources, and of those 5, one, the one you see here colored in blue, is particularly cool. Not only is it particularly cool, but it's also located exactly at the spot where the massive black hole has been located in the galaxy of M31. Why is this so interesting, you could ask? We cannot explain what we're seeing by any of the usual models for emission associated with X-rays coming from black holes. This represents a challenge to our theoretical friends to see if we can find an explanation for what we're seeing.
The giant black holes in the center of the Andromeda and Milky Way galaxies are like dormant volcanoes compared to those in some galaxies. The key difference is the amount of gas available for the black hole to swallow. If there is a huge supply, the power generated by the black hole can be stupendous. This is apparently what is happening in quasars, which produce energy equivalent to that of 1 trillion stars from a small region in the center of a galaxy.
Quasars are fascinating because they're the most powerful sources in the universe. And they push the laws of physics really to the extreme. They have the most supermassive black holes. They give you energy from the whole range of the electromagnetic spectrum. So they can be studied at all wavelengths. And therefore they're very fascinating. Also, we don't know very much about them compared, for example, with stars that have been studied for 30 or 40 years or more.
Chandra will no doubt open a new chapter in our understanding of quasars. With its ability to pinpoint distant quasars at the very edge of the observable universe, it is already shedding light on their role in one of the most enduring mysteries in X-ray astronomy. During the rocket flight that discovered the first X-ray source in 1962, Riccardo Giacconi and his colleagues also discovered that the sky as seen through an X-ray telescope is not dark. Rather, it is bathed in a uniform diffuse glow, a glow called the X-ray background. Astronomers have long suspected that the glow is from quasars that are far, far away. But there was no way to prove this, because the sources could not be brought into focus. Chandra has changed all that.
With Chandra, we now know what these objects are. We've resolved out that glow into many, many, many faint sources. And the questions that we're trying to answer now are, what are these faint sources?
The mystery of the X-ray background is well on its way to being resolved into discrete sources, which we are now resolving into galaxies, quasars, and active galactic nuclei, which are very massive black holes in the centers of galaxies. There are new mysteries beginning to come into fore of objects that don't show up even in the faintest optical photographs.
The riddle of the X-ray background may be solved, but the solution may have revealed a greater mystery. What are these objects? They could be galaxies that are completely surrounded in dust, or infant galaxies that have yet to form stars and are still just huge clouds of hot gas with giant black holes in their centers. Or they could be the most distant galaxies in the universe, whose visible light has been absorbed on its way to us. Or they could be none of the above. As we've seen, giant black holes are notorious for their power to suck matter out of sight. But this is only part of the story.
Black holes pull matter into themselves, and their energy source is this matter which is falling into the black hole. But as part of the processes that go on, black holes can actually eject matter and energy as well. They do this through jets, which in the case of quasars and galaxies can be very large-scale structures that are very concentrated beams of matter and energy that are being thrown out of the black hole. The study of these jets will be very important for learning how we actually convert energy from magnetic fields into particles and back again. We know this process takes place because we see it happening in radio sources and quasars, but the actual theoretical details of the mechanism by which it happens aren't known. And in fact, our X-ray observations are showing us that some of the natural, simple assumptions that are applied can't hold.
Understanding how black holes produce cosmic jets is a major unsolved problem in astronomy today. There is some evidence that they are connected to galaxy clusters, where over time, colliding and merging galaxies may provide the right conditions for supermassive black holes to form. While scientists pursue the mystery of cosmic jets, they also use galaxy clusters as a unique laboratory for studying the dynamics of galaxies in crowds.
While many galaxies appear to be islands of light, completely alone in the universe, in fact they're involved in small groups of galaxies. Our own galaxy, which we call the Milky Way, is in a small group, along with our satellite galaxies, the large and small Magellanic Clouds, the larger galaxy, the Andromeda Galaxy, and many other small galaxies like the Dwingaloo Galaxy. Now, some galaxies, a smaller percentage, are involved in really rich clusters of galaxies, which contain many hundreds of galaxies and stretch over large expanses of space. We used to think because when we looked at them, all we saw were the visible galaxies, that the space between those galaxies was completely empty. But we learned from X-ray observations that in fact that space isn't empty, but it's filled with a very hot, very diffuse gas. This gas is so hot it only emits in X-rays.
Galaxy clusters contain so much of this hot diffuse gas that they are the most massive objects in the universe. The total mass of the hot gas is greater than that of 100 trillion stars. But scientists using Chandra are looking for more.
One of the primary applications with Chandra observations is determining the total mass of a cluster of galaxies. In order to figure out the total mass of a cluster, you need to know the temperature of the gas. The hotter the gas is, the more mass you need to constrain it. And also, the bigger the cluster is, the greater the mass will be. And so Chandra observations give us both simultaneously. We get the image of the cluster, so we can figure out its extent. Plus, we get the spectrum, and we can figure out the temperature.
Observations show there is not enough matter in gas and stars to hold the hot gas in. It should have escaped the cluster long ago. This means that 70% of the matter in the cluster is unaccounted for. What is it? Scientists agree that it must be in some mysterious unseen form called dark matter.
What is this mysterious dark matter? Well, it's really just not known. Could it be some kind of planet-like dark objects, or maybe extremely faint white dwarf stars or black holes, something scientists would call machos? Or could it be some kind of exotic, undiscovered elementary particle, a weakly interacting massive particle, what scientists would call a WIMP? Well, recently a partial answer has been given. A search for machos has been done and completed, and some were found, but not enough to be the entire dark matter. So maybe 20%. So that leaves us with the conclusion that most of the mass of the universe has to be some kind of exotic, WIMP-like particle, or perhaps something even stranger.
Using Chandra and other telescopes, astronomers should soon know how much dark matter the universe contains. A much more difficult problem will be to determine what the dark matter is and the role it played in shaping our universe. It is widely accepted by scientists that the universe emerged from an incredibly hot and dense state about 15 billion years ago. But there are problems. So far, there is no theory that explains how the universe evolved from a hot, dense uniform state to a clumpy universe of galaxies, clusters, and superclusters of galaxies.
The outstanding puzzle is, did the really large-scale things like the clusters of clusters form first and then break up into little galaxies, or did pieces of galaxies form first and then merge together to make galaxies and clusters and larger scale structure? It's called top-down and bottom-up by the people who do it for a living.
The theory favored today is the bottom-up theory. Galaxies formed and then clumped together to form clusters of galaxies, all of which are strung out along a vast network of filaments that are hundreds of millions of light years long. X-ray observations will be especially critical in settling this top-down, bottom-up debate.
With Chandra, we have opportunities to look at the very distant objects and really look at that evolution. We know from our present observations that there is probably a lot of that going on, but until now, there's been no opportunity to study that in detail. We're seeing huge clouds of gas colliding and getting heated as they hit each other. So we're seeing the process of formation of these really large structures.
The observation of merging clusters is evidence in favor of the bottom-up theory. But the formation of clusters takes time. Too many clusters too soon would not fit the picture. Chandra can be used as a time machine to study this evolution. Because it takes billions of years for light to travel across the cosmos, Chandra sees a galaxy cluster 10 billion light years away, the way it was 10 billion years ago. This look into the past will tell us when galaxy clusters first appeared.
Most of the models of how things form say that there should not be vast numbers of clusters far away and long ago. If there are very few clusters, then you haven't learned anything. It's what you expected. If there are vast numbers of distant clusters, then we need to rethink some aspects of how structure formed. I want it to be the most exciting result possible. I want there to be a puzzle.
The search for distant galaxy clusters carries us ever deeper back in time and space. Chandra was made to explore these and other mysterious regions of the universe that hold essential clues to the cosmic drama and our role in it. It was the dreams, vision, skill, cooperation, and dedication of hundreds of men and women that created Chandra, a scientific and technological wonder that is rooted in our need to understand. As it glides silently through space, Chandra is taking us on a grand voyage of discovery, so that we may come to know nature's hottest places and see more clearly that immortal sea which brought us hither. GalaxyOnline.com, Earth's premier science fact and science fiction network. Expand your universe.
Are you getting a TV picture now, Houston? Neil, yes, we are getting a TV picture. You're in our field of view now. That's one small step for man, one